In the final video in this module, we're going to look at a property of a matrix called the determinant, and what happens when the matrix doesn't have linearly independent basis vectors, picking up on the basis vectors we looked at in the last module. Let's go back and look at a simple matrix like A0, 0, D. What this matrix does is it scales space. So if we have our original basis vectors, E1 hat and E2 hat, it scales them out by a factor of A in this direction to A0, and by a factor of D in this direction to 0D. And we call those E1 prime and E2 prime. Now see what I've done to the space. It was originally this size, 1 by 1. And what I've done is I've scaled the space, every vector in the space, by a factor of A this way and by a factor of D this way. And therefore I've scaled the space by a factor of AD. All areas in the space, everything's got bigger by a factor of AD. And I call that the determinant of the transformation matrix. Now, if I instead have a matrix which is A0, BD instead, the same but with a B, what that does is E1 hat stays as it was, it's scaled by a factor of A, but E2 hat goes somewhere different. So E1 hat goes to A0, but E2 goes to BD, somewhere like this, BD. Now, see what's happened to the space. I've gone from being something like this to being something like this. I've made a parallelogram, but the area of the parallelogram is still AD. It's its base times its perpendicular height. So the determinant is still AD of this transformation matrix. Now, if I have a general matrix, ACBD, then it turns the original unit square into a parallelogram like this. It moves this vector to here, this vector to here. Then to find the area of this parallelogram, I'm going to have to do a bit of maths. So I'm going to do that, and then we'll have a look at it in a moment. So I've done the maths, and it's here. And you can do the geometry and puzzle it out for yourself and pause it if you like to verify that I'm correct. But the area of the parallelogram here is actually AD minus BC. And I'm going to denote the operation of finding that area with vertical lines like this, and call that finding the determinant of A, which you probably saw in school. Now in school, when you looked at matrices, you probably saw that you could find the inverse of a matrix like A, B, C, D by flipping the terms on the leading diagonal and taking the minus of the off-diagonal terms for a 2 by 2. So let's do that and see what we get. So when we multiply that out, we get AD minus BC. Interesting. Then on this element here is A minus B minus plus BA. And so we've got A minus B plus BA, so that's 0. When we do this term, we get CD minus CD. And when we do this term here, we get CB times minus B, so that's minus BC, plus AD, so that's AD minus BC. Interesting. So that's the determinant. So if I multiply by 1 over the determinant, AD minus BC, then these terms will become 1, and I'll get the identity matrix. So if this was the matrix A, and I think of this and this together as being A to the minus 1, then I've got this is in fact, when I pre-multiply by 1 over the determinant, is in fact the inverse of A. So we proved here that that determinant, that inverse you learned in school, is in fact correct. But the interesting thing is that this determinant there, this amount that it scales space, if we then take this matrix when we do the flipping around, we haven't changed its scaling of space. We need to undo that scaling and bring it back down to a scale of 1. So the determinant here is what we need to divide the inverse matrix by in order for it to properly be an inverse. Now we could spend another video looking at the extension of the idea of row echelon form to find out how to find determinants in the general case computationally. But this is both tricky to show and it's kind of pointless. knowing how to do the operations isn't a useful skill anymore because we just type det A into our computer and Python or MATLAB will do it for us. From a learning perspective, it doesn't add much to row echelon. Row echelon does actually, which is why we went through it. I'm not going to teach you how to find determinants in the general case. If you want to know, look up QR decomposition and then follow that through, and that's how computationally you go and find it out, or in a linear algebra textbook is the other place to look. That's how you do it in the general case. Now, let's think about this matrix A here. It transforms E1 and E2 hat to 2 points on the same line. It transforms E1 hat to 1, 1, and it transforms E2 hat from there over to 2, 2. And they're both points on the same line. They're just a multiple of each other. They're not linearly independent. What this matrix in fact does is it transforms every point in space on a line. And notice that the determinant of that matrix is going to be 0. If I take AD minus BC, determinant of A is 0, because the area of any area has gone onto a line, and therefore that area is 0. So however you compute it either geometrically or computationally, you get a determinant of 0. So if I had a 3 by 3 matrix with a similar situation describing a 3D space, and if I had the same position where one of the new basis vectors was just a linear multiple of the other two, it wasn't linearly independent, then that would mean the new space was either a plane, or if there was only one independent basis vector, a line like we have here. In either case, the volume enclosed would be 0, so the determinant would be 0. Now let's turn back to our row echelon form and apply that idea. Let's take this set of simultaneous equations, say. You can see that the third row is just the sum of the first two. So row 3 is equal to row 1 plus row 2. And you can see that column 3 is just given by 2 of column 1 plus column 2. If you want to pause for a moment to verify that, but it really is true. So this transformation matrix doesn't describe 3 independent basis vectors. One of them is linearly independent on the other 2. So this doesn't describe a new 3D space. It collapses into a 2D space. So let's see what happens when I try to reduce this to row echelon form. If I take off the first row from the second, okay, so far so good. I've got that, and my ABC stays the same. And I take the first one off the second one. So I've got 12, take 12 off 17, I've got 5. If I then take the first and second ones off the third one, I've now got zeros everywhere here. And if I do that on here, I take 12 and 17 off 29, I get 0 here. So now I've got 0C equals 0, which is sort of true, but not useful. There are an infinite number of solutions for C, in effect. Any value of C would work. So now I can't solve my system of equations anymore. I don't have enough information. So if we're thinking about this from a sort of solving simultaneous equations point of view, my mistake was when I went into the shop to buy apples and bananas and carrots, the third time I went in, I just ordered a copy of my first 2 orders. So I didn't get any new information. And I don't have enough data, therefore, to find out the solution for how much individual apples and bananas and carrots costs. So what we've shown is that where the basis vectors describing the matrix aren't linearly independent, then the determinant is 0, and that means I can't solve the system of simultaneous equations anymore. Which means I can't invert the matrix because I can't take 1 over the determinant either. And that means I'm stuck. This matrix has no inverse. So there are situations where I might want to do a transformation that collapses the number of dimensions in a space, but that will come at a cost. Another way of looking at this is that the inverse matrix lets me undo my transformation. It lets me get from the new vectors to the original vectors. And if I've dumped a dimension by turning a 2D space into a line, I can't undo that anymore. I don't have enough information because I've lost some of it during the transformation. I've lost that extra dimension. So in general, it's worth checking before you propose a new basis vector set and then use a matrix to transform your data vectors, that this is a transformation you can undo by checking that the new basis vectors are linearly independent. So what we've done in this last video, in this module, is look at the determinant how much we grow space. We've also looked at the special case where the determinant is 0, which means that the basis vectors aren't linearly independent, which means the inverse doesn't exist. In this first module on matrices, what we've done so far is define what a matrix is as something that transforms space. We've looked at different archetypes of matrices like rotations and inverses and stretches and shears, and how to combine them by doing successive transformations. Then we've looked at how to solve systems of linear equations by elimination and how to find inverses. And then finally we've looked at determinants and linear independence.